So the next question is a location optimization problem where we have 7 potential locations for establishing fire station, and the objective is that we want to find the minimum number of locations necessary to provide coverage to all areas. So let's say we have 7 regions here, and we want to decide at which one of these locations we want to establish a station. So basically we have 7 decisions to make, A to G, and they are 0 or 1 type of decision. We want to see whether or not we will have a station in region A in optimality, whether or not we want to have a station in region B, and etc. So let me just go here and write it down. So the decisions that we have to make, whether or not establish a station in location I, and I can be A, B, C, D, E, F, and G. So I'm gonna define A. I'm gonna define A, B, all the way to G, 7 variables. These are gonna be 0 or 1 type of decision. 1 means establish a station in location I, basically in either in location, I would say, in location. And then 0 would be do not. So we have 7 decisions to make, and then objective function would be to minimize the total number of established stations, total number of stations to be established, and that we can find with adding up our decision variables A to G. If we don't have any station, if they all take zeros, so this number of stations would be 0. If they all take 1, which basically means that we establish stations in A, B, C, D, E, F, and G, then number of stations would be 7. The objective here in this problem, we want to find the minimum number of stations that can serve the whole region, the whole San Diego region. So in location optimization problems, usually when it comes to constraints, a must to have is that if we go back again to the question, it says find the minimum number of locations necessary to provide coverage to all areas. So this statement, this phrase actually tells us what should be the constraint, at least the first set of constraints. So we want to have coverage to all the regions. So region A. So region A should be covered. This means that in order for region A to be covered, so we have to have either, so if you have a station in region A would be covered. If you have a station in region B, A also would be covered. A station in C can cover region A. A station in G can cover A as well. So regions that can cover A are A, B, C, A, B, C, and G. So these are the covering regions. Covering regions for region A. These are the regions that if we establish a station in them, region A would be covered. So in order for region A to be covered, at least one station should be established in one of these covering regions. So at least one means that the number has to be greater than or equal to 1. Same thing for region B. If we write the same thing for region B, region B can be covered if we have a station in region B, if we have a station in region D, and that's it. B plus B should be greater than or equal to 1. For region C, C plus E should be greater than or equal to 1. For C, C plus E, C plus E. For D, D can be covered if you have a station in D or E or F. D, E, F. E can be covered if we have, E is a little bit strange because E can be covered if we have station in A, B, C, D, F, and G. Only E cannot serve itself. All other regions can serve E. So for D is going to be A plus B plus C plus D plus F plus G greater than or equal to 1 for E, F, and G. For F is going to be E plus F plus G greater than or equal to 1. For G is going to be A plus B, A plus B plus G greater than or equal to 1. So this is the formulation. And then we know that all of them should be, I already defined this binary decisions, binary constraints actually. Now if we come to our Excel, so the first step is to assign empty cells for decision variables, empty cell to decision variables, and as I said, we have 7 decisions to make: A, B, C, D, A to G. So let's assign these 7 cells to them. Objective function is sum of decision variable which basically tells us the number of stations that are established, and then constraints. So we want to cover all these 7 regions. So let me just put the list here. So covering regions. For A, covering regions are sum of A, B, C, and G. So I'm referring to my formulation here, A, B, C, and G. Some of them should be greater than or equal to, let me just, some of them should be greater than or equal to 1. And then this greater than or equal to 1 should be the same for all of them. So I just copy the same thing. But then this one, let me copy the formula too. This one would be different for each region. For region A, we already wrote it. For B is going to be sum of B plus D. For C is going to be equal to C plus E. For D is going to be D plus E plus F. For E is going to be sum of everything except E. For F is going to be EFG, sum of EFG. And then for the last one, for G, is going to be A, B, and G. A, B, and G. And they should all be greater than or equal to 1. So let me go to solver to define it. So we want to minimize the number of stations by changing these variables, and then so let's just make sure that these are good. So we want our decision variables to be binary. That's good. That's how we define it, binary. Okay. And then this one, we want these left hand side to be greater than or equal to the right hand side. So these are good. So I just had it, I just made a mistake, so I had to record the video again. But let's say if we don't have these two guys, let me just delete and then delete this one and just do it again. So add, I want these guys to be greater than right hand sides, and I want my decision variables to be binary. That's all. And then I want to use it, I want to use simplex LP, make constraint non-negative. That's unnecessary since I already defined binary, but let's not change it. And then let's just solve it. Okay. So as you can see here, 1 and 1. So B and E. If we establish our fire station at region B and E, we can serve everything. As you can see, the covering region for each one of those. There's exactly one region that can serve A, exactly one that can serve B, etc. all the way to G. All of them are satisfied, all of them are covered, and then the minimum number is 2 here. So that is the answer. Let me just, because for the next part we may have to change the problem a little bit. So let me paste only values here, and that's okay. And that is the answer to part. So formulation was part A, which you would either put it in paper or on your Excel. And for part B, solve the problem in part A using Excel solver. So this is part B. Part B. And then for part C, it asks to check for an alternative optimal solution. So this is the way we check it for binary problems. So we have to define a set of variables that are equal to 1 in our optimal solutions, and then minus those that are 0 in optimal solution, less than or equal to the number of variables in this set 1. So let me come back here. Let's go here. Let's just go here, and let me just go back to my optimal page. So let me bring it here, sorry. If we just come here, so set of variables in set O, which basically means those are that are taking 1 in my optimal solution. So the constraint, new constraints, for alternative search would be, for alternative search, my new constraints would be B plus E, those that took 1, minus those that took 0, A plus C plus D, A, C, D plus F and G, this should be less than or equal to the number of variables in set O, the number of those variables that took 1 before. So we had 2 of them, B and E, 2 minus 1, 2 minus 1. So here is 1. So I just need to add, for part C, I just need to add, I would call it alternative search. And I want this plus this minus the sum of negative ones. This and this. I want this sum to be less than or equal to 2 minus 1. So the only change would be adding these constraints. So again, we go to solver. Everything is good except that I want to add these new constraints. So this should be less than or equal to 1. Okay. Now if I solve this and if I get the same objective function, that would be an alternative optimal solution. But if I get a worse objective function, that would be my second best answer. So let's just try it and see what happens. Okay. So what happens here is that it's not 2, right? So now with the new constraints, with the new added constraint, I ended up with, so part C. So let me just copy these guys and paste it here. So I can say since minimum number 3, the new solution is not optimal, it's not alternative optimal, and indeed it is second best. It's the second best answer. And that's the answer to this question. Let me just check now. Check to see if you can find an alternative optimal solution. So there is no alternative optimal solution, and we just found the, so here we just found the second best answer.